Today we're going to start part 2, angles in the coordinate plane, and we want to get a couple more definitions that are going to be helpful for us moving forward. The first of those definitions is coterminal angles. Coterminal angles. Now let's do a little etymology here. Let's play with these words. What does the word co usually mean?
Together.
There's two things. Cooperation. There's two things working together. Coterminal. What is terminal? Where have we seen that term before? Terminal. Every angle has an initial side and a terminal side. Right, so coterminal angles are two angles that share a terminal side. Of course, they have to be in standard position. So two angles in standard position that have a common terminal side. All right. Now, these angles have some properties that we are going to discuss. They're important to us. If you don't have your calculators out, grab your calculators and make sure you have those out and ready to kind of do some what-ifs. If you need to jump up and grab one, you can do that also. Angles in standard position that have a common terminal side. All right, so can you think of two angles that are coterminal? Two angles in the coordinate plane that have common terminal side. Can you think of any angles that fit this description? You're thinking something. Just say it. 90 and 450, right? 90 and 450. That works, right? 90 degrees and 450 degrees would work because 90 degrees is just right here. That's 90 degrees. 450 would be all the way around 360 degrees plus 90 more. So 90 degrees and 450 degrees definitely have our coterminal angles. What about if I started here and went all the way back around this way to right there? What would that be? Negative 270 degrees, right? So those are three coterminal angles. Those angles are all coterminal. 450 degrees and negative 270 are coterminal angles with 90 degrees. All right? Let's look at this example. What are the three angles that are listed here? 30 degrees, 390 degrees, and negative 330 degrees. Right? So what is the relationship between these angles? We've got 30 degrees there, negative 330 degrees, and positive 390. How do they relate to each other numerically? They're 360 degrees apart, right? So you add 360 degrees and subtract 360 degrees, right? 30 degrees plus 360 equals 390. And then 30 degrees minus 360 degrees is equal to negative 330. So that's how we can find the two coterminal angles, by adding 360 and subtracting 360. That's what Hattie did with 90 degrees, right? She added 360 and got to 450. She subtracted 360 and got to negative 270, or somebody came up with the other one. All right? So those are coterminal angles. Now, we can, just as a skill, find two angles that are coterminal to the following angles. What would two angles be that are coterminal with 200 degrees? Negative 160, we get that by subtracting 360. And what would another one be? 560, we get that by adding 360 to 200. Right? Bryce, what about negative 100 degrees? What's a coterminal angle to negative 100?
I don't know.
Yeah, you do. Add 360. What do you get? 260, see? And if we subtract 360, what do we get? Negative 460 degrees. So to find coterminal angles, we add 360 and subtract 360. And I'm going to tell you in a minute what the significance of that is, what the significance of coterminal angles is. All right, now, if we're finding angles that are coterminal to radian angles, it's a little bit different, right? What are we going to add and subtract with radian angles? Pi over 3, negative 3 pi over 4. What are we going to add and subtract to get the coterminal angles of these? 2 pi, right? Because pi is 180 degrees. Getting coterminal angles, we add or subtract 360. 2 pi is 360. So I would take this angle, pi over 3, and I want to add 2 pi. And I want to subtract 2 pi. And to do that, I have to get a common denominator, right? What's the common denominator going to be? 3. Got to work with fractions well in this class. That's for sure. So I'm going to get a common denominator in both places. So pi over 3 plus 2 pi over 3 is what? It's pi plus 6 pi. 7 pi, right? 7 pi over 3. And pi over 3 minus 6 pi over 3 is negative 5 pi over 3. We treat pi like a variable, and we treat the numbers in front of it like coefficients. Now, pi is not a variable. It's a number, but it acts like a variable. It's an unknown quantity, really. We can approximate it, but we don't know exactly what it is, so it behaves like a variable. So pi over 3 has, these are the two closest coterminal angles with pi over 3. All right? Negative 3 pi over 4. Negative 3 pi over 4. Again, we would add 2 pi, and we would subtract 2 pi. This time, instead of a common denominator of 3, what is our common denominator going to be? 4. So multiply top and bottom by 4. And that gives us negative 3 pi over 4 plus 8 pi over 4. Negative 3 pi plus 8 pi is 5 pi. And in the bottom, negative 3 pi minus 8 pi is negative 11 pi over 4. So negative 3 pi over 4 has these two coterminal angles. All right, now here's the significance of coterminal angles. Y'all listen, this is a good stuff here. Coterminal angles have the same trig function values. Let me instead of function, same trig ratio values. And here's what we mean by that. Let's go back to that first one that I gave you guys. The sine of 30 degrees is equal to the sine of 360 degrees is equal to the sine of, no, not 360. I messed up. What was the coterminal angle there? Add 360, we get what? 390. And that's equal to the sine of negative 330. How's this helpful to us? How does this help us? What's the definition of the sine? Opposite over hypotenuse, right? In a what kind of thing? In a right triangle. Could 390 degrees be in a right triangle? No way. But 30 is. Is negative 330, can that be the angle of a right triangle? No, but 30 is. And if the coterminal angles are the same, then we can work with those angles and get it. Now let's look at this triangle, because this is one of our what? 30, 60, 90, right? And we have that on the board over there. What's the side ratios for 30, 60, 90? Smallest side is 1, square root of 3, hypotenuse is 2. What's the sine of 30 degrees? It's 1/2, right? So is the sine of 390 degrees. So is the sine of negative 330 degrees. They all have a value of 1/2. And we can get that just by going to our special right triangle. Okay? So coterminal angles have the same trig ratio values, and that helps us. Trig ratios are defined to be the ratios that exist inside right triangles. So we can't really talk about the sine of 200 degrees. We need something else to reference it to. Okay, so if we can find a coterminal angle that's acute or obtuse to 200 degrees, then we're in good shape. If we could find a reference angle, we're also in good shape. So the second thing we're going to define today is a reference angle. Reference angle, by definition, is the smallest angle between the terminal side of the angle and the x-axis. All right? Now, it's important. Two important words here, most important words, smallest and x-axis. X-axis is extremely important. The smallest angle between the terminal side and the x-axis. Okay, that's the reference angle. Now, I made, pardon the overuse of the word, but I made reference to this angle, the reference angle, a couple of days ago in our lesson. I told you this angle is going to be important to us. Remember doing that? I can't remember what the angle we were looking at was, but I said it's going to be important that we be able to find this angle. That's the reference angle. All right, so it's the smallest angle between the terminal side and the x-axis. So let's find a few reference angles here. What would the reference angle for 200 degrees be? We'll find 200 and negative 100. Let me write those down, and then we'll go to we're finding the reference angle for 200 degrees. I want to know what the reference angle is equal to. Let's draw it. (200 degrees) is right there, right? That's 200 degrees. The reference angle is the smallest angle back to the x-axis. That's the reference angle right there that I just put in green. What's the value of that angle? 20. 20 degrees is correct. Okay, now that reference angle creates a, guess what this is? Guess what we call that? It's called the reference triangle. We know a lot about it, don't we? This is 20 degrees, which means that's 70 degrees. That's a good old, it's a 20, 70, 90 right triangle. If we know the angles and one of the sides, we can solve the triangle and find all the values that go along with that. All right? We're not doing that in this particular lesson yet, but we will in just a few minutes. What's the reference angle for negative 100 degrees? Sketch it. Negative 100. It's right here. Right? It's negative 100 degrees. The reference angle is the smallest angle back to the x-axis. So here's the reference angle right there. What's the value of that angle, Bryce?
80.
80. 10 goes back to the y-axis, and that's going to be a tricky thing for us. It's 80 degrees. So it creates this reference triangle over here. This is 80 degrees, this is 10 degrees, and got a 90 degrees. There's a lot we can do with that information. Okay. All right, radians. All right, let's look at the radian 5 pi over 6. 5 pi over 6 and negative 8 pi over 3. Let's find the reference angles for those two things. And anytime you're given a problem in radians, guess where I want your answer as? Radians. Okay? So let's start with 5 pi over 6. The reference angle is going to be equal to, we don't know. What's pi over 6? 30 degrees, right? So 5 pi over 6 is 150 degrees. So 5 pi over 6 is 150. Right? That's 5 pi over 6. Which means this angle right here is what? 30 degrees, but I want to answer in radians. 30 degrees is pi over 6. You're going to be able to do this without converting soon. Promise. You'll just know it's that. Because all the way to 180 is pi, which is 6 pi over 6. Right here we would have pi, which is 6 pi over 6. 5 pi over 6 plus this pi over 6 here gives us 6 pi over 6. So that's a pi over 6 angle. All right, what about negative 8 pi over 3? Pi over 3 is what? Pi over 3 is what? 60. Negative 8 of those is negative 480. Negative 480. So that's negative 360 plus negative 120 more. It's 90 and 30. Gets me right there. It's negative 8 pi over 3. The angle that I'm looking for is this angle right there. So if you think of this in degrees, that was negative 480 degrees, right? Which is 360 plus 120. So what's this going to be in degrees? What is this going to be equal to in degrees? 60 degrees, right? 60 degrees is what in radians? Pi over 3. So the reference angle for 8 pi over 3 is... reference angle is pi over 3. You see any patterns here? See any patterns? I wonder if that's always going to work. Lauren is shaking her head. She's right. It always works. If the denominator of your angle is 2, 3, 4, or 6, and your fraction is simplified, then the reference angle is pi over 2, pi over 3, pi over 4, or pi over 6. All right? And what's the significance of pi over 2, pi over 3, pi over 4, and pi over 6? What's pi over 2? 90 degrees. Pi over 3, 60 degrees. Pi over 4, 45 degrees. Pi over 6 is 30 degrees. So the angles that we're talking about there are 30, 45, 60, and 90. Those are the angles of our special right triangles, 30, 60, 90, or 45, 45, 90. All right, so the reference angle of 6 pi, gosh, I started with something that's not going to work there, 9 pi over 2 is pi over 2. Reference angle of negative 23 pi over 6 is what? Pi over 6. The reference angle of 8 pi over 6 is why is it pi over 3? Because the fraction is not simplified, right? 8 pi over 6 is 4 pi over 3, so the reference angle is pi over 3. So you're going to love radians eventually because of this. This is what makes radians so much easier to work with. One of the things that makes it so much easier to work with than degrees. The reference angle is right in your face. And 90% of the angles that we're going to be working with in this class are going to be pi's over 2, pi's over 3, pi's over 4, pi's over 6. Because that's the special right triangle angles, the special angles. All right. So this is going to come in really, really handy for us. Now here's an important fact, and this is the biggest fact of the day. There is a relationship between the angle and its reference angle. All right, and that relationship is this. The values of the 6 trig ratios, sine, cosine, tangent, cosecant, secant, and cotangent of any angle are the same except for the sign, except maybe positive, negative, as the trig ratios for its reference angle. And we just said that the reference angle is always going to be one of those special angles most of the time. It's going to be 30, 45, 60, or 90. That's the reference angles we're going to be working with. The significance of that is that every reference angle is the angle of a triangle. Right? If it's a reference angle, it's less than 90 degrees, which means it is the angle of a triangle. And we can find the trig ratios for any triangle angle. Can't put 200 degrees in a triangle, but we can put 20 degrees in a triangle. And the sine of 20 degrees is equal to plus or minus the sine of 200 degrees. So we can work with that, okay? So this is a big, big fact. And we're going to use this in just kind of some simple word problems here as we finish up. I'm going to pass something out to you. Did I pass out the sheet yet? Let me pass it out. All right, so here's how we're going to use this fact that we just looked at, that the value of the 6 trig ratios for an angle is the same as the 6 trig ratios for its reference angle, except for maybe plus or minus, to evaluate things like this. Problem number 1 says find the exact value of each of the 6 trig functions if the terminal side of the angle contains the point 3, 4. All right, what do we know about this angle? What's the information that we're given? The side passes through the point 3, 4. We don't have any idea if it's a, first quadrant angle, or if we know it's a first quadrant angle, but we don't know if it's acute or if it's negative, or it's, we just don't know a whole lot about it. 760 something degrees. Who knows? All right. All we know is that it passes through the point 3, 4. Now, what class is this again? Trigonometry, right? What are we measuring in here? Triangles. So the question we're going to ask whenever we approach a word problem is, where is the triangle? Okay. Can you draw a triangle with this information? Start with the point. Can you draw a triangle from that? We can, can't we? Looks like this. Instead of trigonometry, instead of where's Waldo, it's where's the triangle. We're always looking for the triangle in our word problem. Now, can we label this triangle with the information that we're given? We can, can't we? Right? What's the bottom leg of this triangle? The leg that's on the x-axis, excuse me. What's the value of that leg? 3. All right. The vertical leg out there to the side is 4. Because the point is right 3 and up 4, that's the values of the legs, right? And we can use the Pythagorean Theorem. 3 squared plus 4 squared equals c squared. That's 9 plus 16. 25 square root of 25 is 5. And because of that fact that we just learned, the values of the 6 trig ratios are going to be the same for this angle as they are for whatever x is. And again, I have x drawn in there, but x might be this angle. X could be a negative angle that starts here and goes around 3 times. We don't know what x is, but we do know that the terminal side passes through that point, and that's all that we need to know, because the 6 trig ratios are going to be the same as the trig ratios of the reference angle and reference triangle. All right? So what's the sine of x? Y'all are quiet on me. Sine is opposite over hypotenuse. You didn't listen to that song enough. It's in there. Everything you need to know about trig is in that Getting Triggy with It that I sent out. 4/5 is correct. What's the cosine of x? 3/5. Tangent of x is 4/3. These foundational skills of trigonometry. The trig ratios. And then the cosecant is the reciprocal of the sine, so cosecant is 5/4. The secant is the reciprocal of the cosine, so it's 5/3. And the tangent is the reciprocal of the cotangent, and so the cotangent is 3/4. Okay? And we get this because the reference angle is going to have the same value as the regular angle. So really all we need is the reference angle placed in the correct quadrant to find anything we want to find out about the angle. All right, next example. Find the exact values of each of the 6 trig functions if the terminal side of angle x contains the point -5, 12. Now some of you are going to get to this test next Friday or Thursday, and you're going to look at this problem and say, oh my gosh, I forgot how to do this. What are we always looking for in trig? The triangle. You got to go to the triangle. All right, where is the triangle in the problem? Trigonometry. We're measuring triangles. You can write this on the notes page if you want to, or that you don't have to. The triangle here is going to involve the point -5, 12. Again, we don't know anything about this angle. We don't know if it's an obtuse angle or if it goes around, 6 times before it stops. That's all we know, is that the terminal side is right there. And the good news is that's all we need to know, because the trig function or the trig ratios for the angle are going to be the same as the trig ratios for the reference angle. So that reference angle in this case is going to come from this reference triangle. All right? Left and down are negative. Up and right are positive. So if we went left there, we got to have a value of -5 on the triangle. All right. Left and negative. This is going to be really, really important when we're talking about vectors that we have negative. We can have negative quantities in a vector. This vector that we're talking about here would be, if this were a vector, it stops right there, right? The tip is going to be at that point when we get to vectors. The horizontal component of the vector is negative. The vertical component of the vector is positive. So this would be -5 and 12. 5 squared plus 12 squared is 25 plus 144, 169. Square root of 169 is 13, right? This is one of those things I tell my students all the way through Algebra 1, college algebra. I reminded you it's important to know your perfect squares up through 20. This is one of the main reasons it's important. So you can really, really manipulate the quadratic form, the Pythagorean Theorem really quickly. Now we're ready, right? We've got our triangle. We can tell what the 6 trig ratios are. The sine of x is what? 12 over 13. Cosine of x. It's the value of the adjacent leg over the hypotenuse. -5 over 13. Tangent is the opposite over the adjacent, so it's 12 over -5. And then, of course, the 3 reciprocal ratios: cosecant 13 over 12, secant 13 over -5, tangent is -5 over 12. Okay. Now we haven't. I just kind of flew past this fact that came up there. It's very important. The hypotenuse is never negative. All right. When we get to vector applications of this, the hypotenuse represents the force of the vector and the norm of the vector, the magnitude of the vector. It's a distance, so it's always going to be a positive quantity. Okay. Hypotenuse is never negative. All right. What's another observation? What's different about these values than the values in the previous problem? The values in the previous problem were all what? Positive. So in the first quadrant, that's always going to be true. All the trig ratios are positive in the first quadrant. Only the sine is positive in the second quadrant. Okay? Next example. This takes us into the third quadrant, right? Find the exact value of each of the 6 trig functions if the terminal side of the angle is passing through the point -1, -2. Tiny triangle. Make sure you can label it. Draw it big enough to be able to label it. All right, -1, -2. Third quadrant. I don't care if it's to scale. I do care that it's labeled correctly. Right? So that's left 1 and down 2. Left 1 and down 2 are both negative directions, right? So -1 and -2. What's 1 squared plus 2 squared? Pythagorean Theorem. -1 squared plus -2 squared equals the hypotenuse squared. That's 1 plus 4, which is 5, which means C is equal to the square root of 5. What's the sine of that angle? Opposite. It's -2 over square root of 5. It's pretty easy from there, right? Once you get the triangle labeled, it's just kind of opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. You just got to be careful with the SIGN sign of the values of the ratios. And then tangent is equal to the opposite over the adjacent. That's -2 over -1, which is 2. All right, I'm going to fly through these because we need to get to these, at least 2 of these next 3 before the bell catches us. Okay? Now, as a note, in the first quadrant, all 6 ratios were positive. In the second quadrant, only the sine and the cosecant were positive. In the third quadrant, what's positive? Tangent and cotangent. All right? Next example says, find the exact value of each of the remaining trig functions if the sine of x, the sine of our angle, is equal to 4/5, and our angle is in the first quadrant. Now, what's the important question in trig? Where's the triangle? Where's this triangle? In quadrant 1. So start by just drawing a triangle in quadrant 1. That's what we're working with. Where is the triangle? We're measuring triangles in trigonometry. Where is the triangle in the problem? This particular triangle is in quadrant 1. The reference angle is in quadrant 1. Do we have enough information given here to label this triangle? We do. What's given to us? The sine, which is the opposite over hypotenuse. So the opposite value is 4. The hypotenuse is 5. The missing leg is 3. Look at that. Trig award coming soon. Okay. Now, can you do the 6 ratios from there? You can, can't you? I'm going to leave that for you to finish. Let's go and get this next example. All right, but that's the trig ratios that you need to finish. Find the exact values of each of these remaining 5 trig functions if we're told that the cosine of our angle x is -5 over 13, and x is in the second quadrant. Where's our angle? Where's our triangle? Second quadrant. So draw a triangle in the second quadrant. Always, the triangle always goes back to the x-axis. The reference triangle and the reference angle always refers back to the x-axis. What is cosine? Adjacent over hypotenuse, right? The adjacent side is -5. Hypotenuse is always positive. 5 squared plus b squared equals 13 squared. That's 25 plus b squared equals 169. That's right, Bryce. And then you get a value of 12 for that side. And now can we do the 6 trig ratios? Sine is 12 over 13. Cosine is -5 over 13. Tangent is 12 over -5. And then the 3 reciprocal ratios are that. Okay, I'm going to let you fill in those blanks. Let's jump to this last one. This one's a little trickier. You got to be careful with this one. Find the exact value of each of the remaining 5 trig functions if the tangent of x is 4/3 and x is an element of quadrant 3. So where is the triangle? Quadrant 3. You're going to be asking that question all semester. Where is the triangle? Can we draw a triangle from the picture? How do we use what we know about triangles to answer the question? Tangent is opposite over adjacent. Okay? So would it be correct to write 4 here and 3 here? Why is that not correct? Because they're both negative directions, right? Left and down are negative. Up and right are positive. So this is going to be -3 and -4. Which, of course, negative divided by negative would give us a positive tangent value. What's the value of the hypotenuse? -3 squared plus -4 squared. That's 9 plus 16, which is 25. The square root of 25 is 5, the hypotenuse is always a positive quantity. All right, and from there we can find the 6 trig ratios. Sine is 4/5, negative 4/5. Cosine is negative 3/5. We're given the tangent, and so the reciprocal values come from those 3 things. All right, now we'll finish this lesson tomorrow. I apologize